This hammer has enough energy to deform the brick past its elastic limit. I'd hate to absorb the energy of that hammer with my chest, but I don't mind receiving its momentum. We're going to show you an example of a collision. The weight of this brick is 180 newtons. It's not small, but it's negligible compared to the large forces between the hammer and the brick. Obviously, I analysed this collision before doing the experiment, and we'll see that analysis later on. But first, we're going to look at the most general and the most elegant form of Newton's laws. And in order to do that, we'll have to define momentum. For a particle, the momentum p is its mass times its velocity. For a finite body or a system of masses, the momentum is the total mass times the velocity of the centre of mass. Note that momentum is a vector. We can now write the generalised form of Newton's second law. The total external force acting on a system equals the time rate of change of its momentum. Differentiating, we see that, if the mass is constant, we recover the simple form of Newton's second law. Integrating, we see that momentum is changed by the integral of force over time. This change is called the impulse, I. Compare momentum with the kinetic energy, which is changed by the integral of force over displacement. Newton's second law can now be restated as a conservation principle. If the external forces on a system are zero, the momentum is conserved. Note the conditional clause. In general, an object's momentum is not conserved. This car's momentum is zero at first, then it's large and to the right. Its change in momentum came from the force exerted on it by the ground. However, if I consider the Earth and the car as a system, then the forces between them are internal, so the Earth's change in momentum cancels out the car's. In space, where there is nothing to push against, rocket engines use momentum exchange. A small mass of exhaust at high velocity in one direction gives the spacecraft an equal change of momentum in the opposite direction. Because momentum is a vector, we can apply that argument in different directions. Here, the external forces in the x direction are small, so the x component of momentum is approximately conserved. However, the y component of momentum of the hammer and the skateboard is not conserved because of the external forces in the y direction. The normal force is quite large during impact. A collision is an interaction over a relatively short time, during which the external forces are small compared to the internal forces. This collision occurs over a few tenths of a second. Notice that the force on the car is large enough to change its shape very substantially. We estimate about 400 kilonewtons. During the collision between two cars, external forces do act. The cars have weight, and the road exerts normal and friction forces, all of which may be 10 kilonewtons or so. However, these forces are negligible compared with the hundreds of kilonewtons between the cars. Further, because the collision occurs over a small time, the external forces produce little acceleration of the centre of mass. Therefore, during a collision, if the external forces are negligible in any direction, the momentum is conserved in that direction. Another way of writing the conservation of momentum uses the centre of mass of the colliding bodies. For any closed system, we can write total external force equals total mass times the acceleration of the centre of mass, or total external force equals time derivative of the momentum of the centre of mass. So, if external forces are negligible, the velocity of the centre of mass is constant. For two equal masses, the centre of mass lies halfway between them. So let's watch the centre of mass. Double one of the masses and the centre of mass lies 1/3 of the way along their separation. These collisions can tell us something about mechanical energy. Because the centre of mass does not accelerate, the kinetic energy of the centre of mass is not lost. However, we can lose the kinetic energy associated with motion relative to the centre of mass. In an elastic collision, no kinetic energy is lost. What happens in these elastic collisions is that the kinetic energy of motion relative to the centre of mass is briefly converted into potential energy of the springs, then back into kinetic energy. We replace the spring with putty, and all of the kinetic energy relative to the centre of mass is lost. After a completely inelastic collision, all motion relative to the centre of mass is zero. Let's look at that last collision again, but from a frame of reference moving with the centre of mass. In that frame, all the kinetic energy is lost. Most collisions are partly inelastic. Steel is very elastic in the physical sense, so these collisions lose proportionally less energy. And collisions between molecules are usually completely elastic. So, momentum is sometimes conserved. Remember too that mechanical energy is sometimes conserved. Knowing when to use which principle is rather important. How to measure the speed of this golf ball without a high-speed camera. Here it has a completely inelastic collision with a pendulum. During the collision, external forces in the horizontal direction are negligible, so momentum is conserved. During the collision, friction does work to keep the ball in the cup, so mechanical energy is lost. After the collision, the external forces from the pendulum support and gravity are not negligible. That's why the pendulum loses its momentum and stops. However, non-conservative forces do no work, so mechanical energy is conserved in this phase. Eliminating Vx2 from equations 1 and 2, we can calculate the speed of the ball from the height to which the pendulum rises or from the maximum angle. It's important in physics to recognize similarities. The golf ball problem is rather like the hammer-brick problem with which we began. In each case, a small, fast object has an inelastic collision with a larger mass. Conservation of momentum slows them down. Afterwards, there is a phase of approximate conservation of mechanical energy. In the case of the brick, its kinetic energy is converted into potential energy stored in the chest, which acts like a spring with a constant 30 kilonewtons per metre. Here, a similar analysis, done before the experiment, allowed me to estimate how far my chest would be deformed after the collision. To analyse two-dimensional collisions, remember that momentum is a vector, and that if the external forces are negligible in any direction, the momentum is conserved in that direction. Conservation of momentum in the x and y directions gives us two scalar equations. However, the final velocities have magnitudes and directions, so there are four unknowns. If the collision is elastic, that gives one more equation. Details of the collision geometry, for instance involving the impact parameter, b, can give another. Momentum conservation is a powerful principle, and it's a general way of writing all three of Newton's laws. As with conservation of mechanical energy, however, you must be careful when you use it.